computational chemists! I'm your new host, Zach. Up until now, we've been using Python's built-in tools, but when we want to handle heavy data manipulation or generate publication-quality graphs, we need to step outside Python's core library. Think of Python's standard library like your basic lab bench. It has a beaker and a stirring rod. But if you need an HPLC machine or a high-precision pH meter, you have to request external equipment from the stockroom. In Python, that stockroom is called PyPI, and we bring equipment to our bench using the import statement. Let's look at the two ways to bring tools into our script. If we want an entire library, we import it and give it a convenient nickname, an alias, using the as keyword. For example, import NumPy as NP. Import Matplotlib.pyplot as PLT. Here, we are importing the entire NumPy library for fast numerical math and the PyPlot submodule from Matplotlib for graphing. Instead of typing out matplotlib.pyplot every single time, we just type PLT. Pro tip, only import what you need. Importing a massive library when you only need a single function wastes system memory and slows down your scientific simulations. Before we translate our chemistry into Python, let's visualize the exact wet lab experiment we are simulating today. Imagine you are standing at the bench. In your Erlenmeyer flask, you have measured out exactly 25 milliliters of a 0.1 molar hydrochloric acid, HCl solution, a strong acid. Positioned right above it is your burette, filled to the zero mark with 0.1 molar sodium hydroxide, NaOH, our strong base titrant. Our goal is to simulate dripping that base into the flask, tracking the dramatic pH changes as we approach and pass the equivalence point. Now, let's dive into our script. We start by defining our chemical universe using data structures we already know. Tuples! Why choose tuples over lists here? Because our starting experimental design shouldn't change mid-run. Tuples are immutable. They cannot be altered accidentally by a rogue line of code later on. Our acid tuple stores the identity, concentration in molar, and volume in liters. Notice we use 0.025 liters instead of 25 milliliters right here, so our SI units match up perfectly for standard molarity calculations later. Next, we establish our loop controls to dictate how our virtual burette behaves. We set our step volume to 0.0005 liters, which is like adding our base in precise half milliliter increments, and tell the simulation to stop once the burette has delivered a maximum of 50 milliliters or 0.05 liters. Finally, we initialize two empty lists, volumes added and pH values. Unlike our constants, these must be mutable because we will continuously append data points to them with every virtual drop we add. Here is the heart of our computational engine, a custom function that determines the pH at any given volume of added base, VB. First, it calculates the instantaneous moles of acid and base present. Moles acid equals acid 1 times acid 2, moles base equals base 1 times VB. Then, we enter a three-way conditional branch that mimics the chemical reality of our flask. Case 1, excess acid. If we haven't added enough base to neutralize the acid is in excess. We calculate the remaining hydronium concentration by subtracting the moles of base from the moles of acid, dividing by the total volume, and passing it to numpy's .np.log10 function. Notice the NP prefix? That's us calling our imported stockroom tool. Case 2, the equivalence point. Why didn't I use elif moles base equals moles acid? Because computers struggle with precise floating point decimal math. Instead, we check if the difference between our moles is less than the increment of moles of the base. If it matches, we assume we are at the equivalence point, so the pH of a strong acid, strong base mixture is perfectly 7.0. Case 3, excess base. Once the moles of base exceed the acid, we switch to tracking excess hydroxide concentration, OH negative ion. Compute the POH and subtract it from 14 to return our final pH value. With our function constructed, we use a simple while loop to incrementally drip our base into the virtual flask, scaling our volume stored to milliliters so it makes intuitive sense on a graph. Now, let's use Matplotlib to instantly visualize our hard-earned numerical arrays. Look how clean this setup is. We initiate a canvas using plt.figure, plot our values with a green line marked with points, and use plt.axvline to drop a clean dashed vertical red line right at our theoretical equivalence point, 25 milliliters. Add some axis labels, turn on the grid so we can read the inflection points easily, and call plt.show. And there you have it! In under 50 lines of code, you've imported specialized engineering libraries, set up an immutable chemical framework, mapped out a physical function, and plotted a perfect, smooth titration curve. Try altering the code to simulate a 0.05 molar solution instead, and see how the result shifts. Drop your findings or any coding bugs you encounter in the comments below. Don't forget to smash that like button, subscribe for more computational chemistry insights, and keep coding!